What's the state of math fluency in this country? Well, this is one of the early studies we did comparing regular ed students and special ed students. Now this is accuracy on addition. The number of correct facts. We didn't count time. This is just accuracy. And what we see consistently is kids are very accurate. That's not the problem. Accuracy is not the problem. Even with special ed students, at age 7, they're over 50% accurate. By age 8, about 65. But by age 9, they're up around 90% accurate, and they continue, all right, right through age 14. Regular ed students are a little faster, all right? Now, when we now look at fluent facts, so the number of fluent facts, this is again an addition, we get a very different picture. We start out somewhere less than 20 for both regular and special ed students, and then you start seeing that discrepancy between the regular and special ed students. Now, look carefully at this. The special ed students at age 14, we're talking about middle school kids, are right at 50 facts, all right? Which facts are those? Zeros, ones, some doubles, and a few twos, right? Now, they never move beyond that. They get stuck pretty much in all operations at about that level. Now, if you look at the regular ed students at age 14, they're up around about 76 fluent facts, all right? That's terrible. That is terrible. Those kids should be fluent down here around age 9, and that doesn't happen in this country, all right? Our kids are not being fluent. Now, if you look at Asian countries, that's not true. You'll find those kids at age 8 or 9 will be almost at 100% in terms of number of fluent facts, about 100, and they continue that right on through. They don't worry about that in schools. All right, I spent a semester in Japan studying Japanese children, and that's exactly what I found, is those kids are fluent. Now, I'm not going to go into all the social reasons that goes on, but they're not worrying about the things that we're worrying about in this country. Those kids are fluent when they come to school. Now, in a most recent study, this is a 2006 study, we looked at 315, a large number of 4th through 8th grade at-risk and special ed students. Of those 315, we gave them a paper and pencil randomly distributed sheet to look at number of facts that they could do per minute. Only 40 of those 315 students could provide more than 40 correct answers to randomly presented addition facts in a minute. Only 40. That is terrible. I thought it would be much higher than that. I was wrong. All right. We then took these 40 and gave them a chronometric analysis. I wanted to find out how many of these kids are false positives. In other words, they appear to be fluent, but they're not. All right. So of those 40, once we did a chronometric analysis, how many of those kids were fluent? Any guesses? One. 1 out of 40. So out of 315 kids that we looked at, grades 4 through 8, we found one student who was fluent in all 100 addition facts. 3 of them had either 95 to 100 facts. So I would say 3 are close to fluent, and then it dropped way off from there. So we're not building fluency in these kids, okay? And this was this is a large scale study. So how do we develop fluency? Well, before fluency can be developed, we've got to move information out of working memory into long-term storage. That's the only way it can be done. It has to be retrieved, not processed in working memory. Now, the way that experts develop fluency is through something called deliberate practice, all right, which is different than what we typically do in schools. In schools, we do what I call simple drill and practice, all right? And simple drill and practice is good for one thing, and that is it simply speeds up information already stored in long-term memory. The more you practice something already stored, the faster it retrieves. There's actually, you actually strengthen the neural pathways when you do that, all right? Randomized drill and practice is not good for moving information from working to long-term memory, all right? And typically that's what we do. We randomly present facts to kids in larger sets than they can hold in working memory, and that's the problem. Deliberate practice, on the other hand, differs. In deliberate practice, we look at activities that are explicitly intended to improve performance, all right? So we want to improve that storage and retrieval, that reach for objectives just beyond one's level of competence. Now what this means is we know where that student is functioning and we want to push them slightly beyond that, okay? If we don't know where that student is functioning, and we're giving them information that they're not ready for, they're going to fail. And that's what we find in schools. We just don't know exactly where those kids are functioning. Provide immediate feedback on results. In other words, every response should get feedback. Are you correct? And if you're not correct, what's wrong? So you give feedback. And then lastly, involves high levels of repetition. I'm talking about very high levels of repetition, hundreds of trials, not tens of trials, okay? And we know now, since, for the last 10 to 15 years, looking at experts, that all experts spend a lot of time in deliberate practice, whether we're talking about, athletes, chess masters, physicists, people who reach very high levels of performance spend a lot of time in deliberate practice. And that's what separates experts from non-experts, is what the amount of time that they spend. Now, if we talk about fluency, okay, again, we've got to look at that information stored in memory, retrieved accurately and quickly without hesitation. That's really what we're looking at. And that occurs with it occurs in math, it occurs in reading, it occurs in spelling. All those foundational skills require that skill. Now, we talked a little bit about working memory, and this is where we think the real bottleneck is for struggling students. It's in that working memory and the way we do it, because working memory is governed by something called the 7 ± 2 rule. And if you've ever studied psych, you probably learned this. George Miller in the 50s said that the rule is we can process about 7 ± 2 chunks of information before we reach cognitive overload. Now, the operative thing there is chunks, all right? Chunks can be fairly large pieces, or for the kids that we're talking about, it's digits, because each digit would be a chunk in that case. Now, when Miller did this work, he did it with his graduate students at Harvard, all right? He wasn't using elementary age struggling students. Since then, we found that for struggling students, well, for all students, but we know that students between the ages of 5 and 14, the rule is more like 5 ± 2. So their working memory capacity, or their processing capacity, is less than what yours or mine is. So they start reaching cognitive overload at about 7 chunks of information, all right? Now, let's do a little working memory test. It's early in the morning. You should do really well at this. I'm simply going to give you a number to look at, all right? All you have to do is look at that number, and what it'll do, it'll come through your reticular activating system into your immediate memory and right to working memory, okay? I'll give you about 3 seconds. All you have to do is tell me what the number is. Here we go. What was that number? 2571325. That was easy, right? There were 7 digits there, unrelated to one another. Unless you see some pattern in there you recognize, it would be 7 chunks of information, okay? Now, everyone can do that without any difficulty. Let's look at one more number. Same thing. Here we go. I gave you a little longer. What was that one? I gave you more time. Come on. 615-724-639. Why couldn't you do that?
Say it louder.
That's right. You got to say it louder, right? It's simply that it exceeds what we as humans can hold in working memory at any one time. There are 10 digits there, and it's just hard to do. Now, we can all learn this number. That's simply a telephone number. And if, for example, you're from Nashville, did you know that? Did you recognize that? Yeah. Okay. 615 is the area code in Nashville. So Scott probably chunked that, looked at the other. Did you get it? Were you able to do it? Say yes. Oh, darn. Anyway, by chunking, it would be much, much easier to do that. But the point here is we all have limitations of working memory. Kids have more limitations than we do, so we've got to reduce that amount of information they're dealing with if we want to be able to hold it in working memory, rehearse it, and move it to long-term memory. And that's really what happens. So it's that limitations of working memory where it's incumbent upon us now to help these kids overcome this problem.